Hello, everyone, and welcome back. We're looking at 732, which is more solving of differential equations. Now, let's recall in the last video what a differential equation is. So a differential equation is just the derivative equation. So we're looking at the derivative or the instant rate of change, right, at that moment, if you could freeze time. All right. So typically in these problems, you might be given a differential equation such as dy dx equals 2x, and then the idea is what's the original equation y that you're in reference to. And the way we talked about that is the idea that you have to separate the variables by getting all the variables that are like on one side and the other on the other side, and then you can integrate. We'd say the integral of dy with respect to y would just be y, and the integral of 2x dx, well, technically that would be y plus some constant c, and this would be 2 times x squared over 2 plus some constant c. But you'll see as I keep doing these videos this week, that constant c, I'm always going to move to the other side and just combine those constants. So I'm going to end up leaving my answer as just x squared plus c. All right, so again, that might be like c1, c2, and when I combine these over, I just make some constant c because I know there'll be just some number there. So the idea of what we talked about last video is given a differential equation, you can talk about the function that it's describing the rate of, but there are infinitely many possible functions, okay, because of that plus c. And there's different ways that come up as well. Now, I do want to talk about two applications, pretty famous ones to make sure you're aware of them, of differentials popping up. Differential equations. Okay. Now the first one is, let's say we are talking about, we have rabbits because rabbits are very popular in this curriculum. Let's say that they're growing at a rate, and I'll call R, of 0.01 new rabbits per week. Okay. Now we could talk about the rate at which the population is changing. So if I have P represent population of the rabbits and T will represent time per week, I guess, in weeks, then we could say that the rate at which the population is changing in relation to time. Now that's what we're going to talk about. So before we get to this, let me give a few examples. So let's say when the population is at, 1,000 rabbits, then that would imply that the rate at which rabbits are growing per week, the rate at which there's new rabbits per week would be 1,000 times 0.01, which would be equivalent to saying 10 new rabbits per week at that moment. Similarly, if I kept going and said, hey, what if the population is at 10,000 rabbits? Well, that would imply that 10,000 times 0.01 would be 100 new rabbits per week. So the idea here is you can see that as the population changes, the rate is also changing, but the rate is changing in relation to the population. So if we were to talk about the change in the population of rabbits relative to time, it is changing in relation to the population P. If the population's 1,000, the rate's 10. Population's 10,000, the rate is 100. Well, the idea that these are changing, but they are related. So if the population changes, this also changes. Now, how are they related? They're related by some constant, which I'll call R here, which is what we used here for the rate. And that constant, well, there can be a lot of different constants there, which is kind of like the constant we've been hitting at. So there's a differential there. Now, another one example I want to show you is a very famous one. This is the first problem that I want you guys to see. It's Newton's law of cooling, one of the applications that you need to be exposed to as a calculus student. And by the way, BT dubs, number 107 in your book, I don't know if it's in the textbook, but in the ebook, the starting soda temp, use approximately 48 degrees Fahrenheit. And I say it because in the ebook it's missing. At least in my ebook. I assume we have the same ebook in that regard. I just have an extra tab of teacher stuff. Okay. But let's look at Newton's law of cooling. So just a little note to yourself when doing that problem is, let's say that I buy a iced latte and I take it home for my wife. Okay. But it's a hot day out, and it takes a while to get home, per se. Maybe there's traffic, who knows. But we'll say that the temperature in my car is a scorching 95 degrees Fahrenheit. Okay. Now, by the time I take it home and say, time I take it home, that iced latte is going to get warmer. And if my wife wanted it cold, well, sorry, it might not be as cold as when you first got it. Now, what's the math that's following here? It's following what's called Newton's law of cooling. And if I give you a visual of this, we talk about time, I'm going to call this little t, and we talk about the temperature, big T, in degrees Fahrenheit. Well, 95 degrees will represent we'll call it the room temp, okay, R. And then the iced latte started at, let's say it started at 50 degrees Fahrenheit, pretty cold, all right? Well, what's going to happen is as time goes on, this is going to get warmer, but how is it going to get warmer? Well, it's going to get warmer in the beginning a lot faster than over time as it gets slower and slower approaching that room temp. So if we talk about the rate at which the temperature is changing in relation to time, you can see that it's changing along this time at every given moment, because again, the derivative is at a particular moment. Well, how is it changing? It's changing in relation to the difference between the room temp and the, I'll call it my iced latte. We'll call I the iced latte temp. Well, it's changing in relation to R minus I. Right? If the difference between them, like say, give it a little bit more, T equals 0, then the difference between them was 45 degrees. Well, at T equals 1, it's going to speed up a little bit. Maybe it'll be at 75 already. So at T equals 1, then it would be a difference of 20 degrees. And at T equals 2, well, now it's maybe at 85. Well, then it's a difference of 10 degrees. And at T equals 3, it'd be a difference of, 5 degrees. But it's going to keep getting smaller and smaller and smaller. So the idea is that the rate at which the temperature is changing according to time at any given moment is related to the temperature between these. Now, how is it related? It's going to be related by some constant C. Now, I believe I'm going to use the same constant they have, which is K. This is your constant of proportionality and how those two are related. Proportionality. And we're going to skip the problem this year due to this environment about showing you where that constant comes from and how these are related. But the idea that I'm trying to get you to show is that the rate at which it's changing is related directly to the difference in temperature between these two. And then we can study that differential. So those are some applications of it. And I did want to expose you to Newton's law of cooling as you do that problem yourself. Now, big idea though for you in calculus and what you'd be asked is still the idea of still solving these. So let me just show you a few more solving differentials. And hopefully this helps you. So Get a new paper here. Solving differentials. Let's move that one over. Example 1, let's say you're given a differential equation of x minus 3. Example 2, let's say you're given a differential equation of a y minus 3. Example 3, let's say you're given a differential equation of e to the y. Okay, so separate the variables. We'd have dy equals x minus 3 dx. Integrate both sides, and if we integrate y, we'll get dy, we'll get y is equal to the integral of x minus 3, which would be x squared over 2 minus 3x, and then plus some constant c, which again, I'm not putting plus c on both sides because that c on the left side will just combine with the c on the right side to just some constant c. And there's your answer for the first one. And it's a good habit to check these because, again, these are tricky. Solving differential equations is not that easy. They can get very complex very quickly. And there's a lot of different orders and degrees. And that's why, again, it's a very big field in the mathematics world right now. So if we check this one, we're going to get dy dx is equal to, that 2 would come in front. So you'd have 2 over 2x minus 3 and then plus 0, which simplifying gets us that x minus 3. So there's your first example. But this one here, separating variables, we'd have dy, and we're going to have to divide by that y minus 3 to both sides, equals dx. Integrating both sides, the integral of 1 over y minus 3 is going to be the natural log of y minus 3 is equal to x, and then plus that constant c. We're going to change this into its exponential form by writing e to the x plus c equals the absolute value, of y minus 3. You can get rid of the absolute value by accounting for the plus or minus there. And then we can rewrite this, if I go a little bit slower here, as e to the x times e to the c, which again, all of this is just some number. So I'm going to write it as c e to the x equals y minus 3. And then I'll add the 3 over to give my final answer of plus or minus c e to the x plus 3. And there's the function that dy dx is talking about the rate of. Checking really quick, taking the derivative to see if we get the same function. We'll have dy dx is equal to the derivative of ce to the x will just be ce to the x because the derivative in exponential is itself, plus the derivative of 3 is 0, so then we'd have plus 0. Okay. Now, notice that ce to the x, if I was to use this equation up here, ce to the x is equivalent to y minus 3. So if I resubstitute that back in, I'd get dy dx is equal to y minus 3, which is my original differential equation. And the very last one, dy dx equals e to the y. If we separate it, we'd have dy over e to the y is equal to dx. I can rewrite this as e to the negative y dy equals dx. Be a little bit easier to differentiate here. Integrate here. So if we integrate both sides, the integral of e to the y, well, since the derivative of e to the y is just the function itself, that means the antiderivative is going to be e to the negative y. But because when you take the derivative of this, because of the chain rule, which would produce a negative, you have to account for that and put a negative in front there, equals integral of dx will be x, and then we'll account with that plus c. Okay. Doing a little bit of algebra here, we get e to the negative y equals negative x plus c. Now notice the way I'm treating this is that c I'm treating as some number now. So I'm going to treat it like a number as I go about all of this. Okay, so negative and all of that would be together. And then we're going to rewrite this as a natural log. So this would be the same as saying natural log of e to the negative x plus c is equal to negative y. Okay. And then bring that negative to the other side. So we'd have negative natural log of negative x plus c. And I believe that's your answer there. Checking this one. Taking the derivative of both sides, we'd have dy dx is going to equal negative, and the derivative of a natural log is 1 over natural log of the base, which natural log of e is 1 times the function itself. So then we'd have a negative x plus c, and because of chain rule, we'd have a negative 1 there. So rewriting this, we'd have dy dx equals 1 over negative x plus c. Now, how is this the same as e to the y? Now, little manipulation right here is when we had y equals negative natural log of negative x plus c, we can rewrite this as natural log of negative x plus c to the negative 1. Because remember, with logs, that multiple in front you can make as an exponent. Which, how does that help us here, is we could rewrite this as e to the y equals negative x plus c to the negative 1, which is going to equal e to y equals negative 1 over negative x plus c. And notice, this right here is what we have here, so this whole thing equals e to the y. And that's how that works out. Right. So a little bit of applications of differentials and a little bit more solving, because that, again, is the skill that we're going to work on. Okay, hope you can follow that and hope you can try it yourself and get the right answers. All right, if you have any questions, just make sure you stop by after office hours or ask. All right, bye-bye.